Alright, hell yeah. Material mechanics, I've solved this problem twice. Well, once, and then I just explained how you can use change in length. So we have 40 meters of length, and we got slack in one. And so here's our equations that we use. We use that strength is force over area and then stretch. So we have a strength and stretch equation. This is stress, this is strain. And then we have a relationship between them. And it says these cables can only take a PSI, a stress of 500 megapascals. So we know that one. We know the area of the cables. We know that one. So even just right off the bat, we could figure out the max. If we're saying just this is the max force, you know what I mean? We could say, the max stress. Well, we can find the max force in one of the cables. And that's what I explained in the other video, but then I didn't solve the actual problem because I already did that in a previous video. But then we can go over here to the change in length equation. It's just when you're getting into material mechanics, you might not... I don't know. Me, I just didn't like the idea that this was called strain. I don't like the symbol, you know what I mean? And then so you just get like, I just don't like it. But the fact that this is change in length and it has everything to do with how if you have a rope, you can only stretch it so much before you reach that max force. So that max force is synonymous with the max stretch. And those two are related. Even though stretch is a very small, like change in length is a very small number, and force might be a very large number, those two are equal. You could say force is equal to change in length, but then you would have to have some sort of constant to make those. So we have, this is the big number, this is a really tiny number, strain, and then so we have an even larger number, modulus of elasticity, especially when you're working with metals. This thing is just a really big number, and it equates these two things. Okay, so those are our three equations, and you can just manipulate them any way to get whatever you want. So in this problem, we wanted to know the change in length based on that max stress times that length of the 40 meters divided by the modulus of elasticity. And damn it, I didn't put the modulus of elasticity, but it's 160 gigapascals. You know what I mean? So that's the other thing. This is 160 times 10 to the 9. This is 500 times 10 to the 6. Okay, so you know what I mean? So what are we trying to find? Well, we're trying to find the change in length of one. I just isolate. I'm just going to take one of these ropes or cables, and then I just want to know what its max change in length could be before it starts to go plastic. And so I realized that, hey, they're giving me this, so I should have circled this too. I know E, so there you go. So like right here, and then I go over to E and I already know the length. So I put this into there, and then I can solve for change in length. So that's what we're doing. We're saying this is stress times modulus of elasticity, change in length divided by length. And that's the equation we get right here. Then we can rearrange to just solve for change in length. And that's what we do. So now we have one characteristic, that if one of these cables can only take a change in length of 0.25. But this is why this makes it a two-star problem, is that they're saying, well, we have 100 millimeters of slack. So by the time this cable reaches its max length, the other cable already stretched 25 millimeters. But the cool thing about change in length is it doesn't matter. That first cable, if you change its change in length by 125 millimeters, it is already producing the max force. So then you can say, hey, this is force over area, this is change in length over length, and this is E, and then you can solve for this change in length. So change in length is FL over EA, and then you can rearrange and get the force equation that says force, and write it like this, EA divided by L change in length, because this is synonymous with the spring equation that says force of a spring is equal to some sort of spring constant times its change in length. So now, even though that second cable is stretched 25 millimeters, that first cable, just because it's stretched 125 by observation, we can say that its max force is EA over L change in length, which is 24,000 newtons. But then in that previous problem, I just kind of left it at that, and then I was just talking about the change in lengths. But obviously that other rope is changed in length by 25 millimeters. So it also will have a force, EA over L, times its change in length, which would be 4,800 newtons. So when this first cable is at its max at 125 millimeters of stretch, the other cable is also stretched, and this has a force of 24, this has a force of 4,800, so you add those together. So at the 125 millimeter mark, you have a total force of 28,800. Okay. And then this is just maxed out. It can't produce any more, but now you have the point where this other cable gets maxed out. In another 100 millimeters, after this point, it's going to get maxed out. So we go to 225, and then when everything is maxed out in the system, it can only be one number, just the maximum number. So if you go over here, the maximum number is this times area, and you get that max number of 24,000. So each cable can do 24,000. Double that is 48. So that's going to be the max number there. There's only one other key area that happens is like, well, you have 100 millimeters of slack, so let's just stretch that first cable to 100 millimeters. You know what I mean? It's not at its max, but we want to know the force in that. So we can do the same thing. The force is that spring constant times the change in length. So we're going to go EA over L, and then we're going to put in, 100 millimeters here, so 0.1 millimeters, and we get this 19,200 newtons. So those are the those are the places where. So and then they said draw a graph. So at 0 weight in that bucket, kind of go back to like what they're saying. So with 0 weight in the bucket, we have 0 change in length, visible. But then when we go up to that first 100 millimeters of change in length, now there's no more slack in this rope, and this will have a force of 19,000 or whatever that was. And then, but once this first cord gets maxed out, we said it was going to be 24, but plus that 4,800. So now we have like a what was this? This is 28,800 newtons right there. And then when they're both maxed out, then it's going to be 48. But then, kind of the take-home point is they want you to draw this graph, and they want you to see that the slope of this line is just EA over L. And that's what we should expect because, like I said, we have a force equation that's... Materials are just like a spring. And if you're a physicist, you're like, oh, hell yeah, I know exactly what springs do. I don't think that helps engineering students because all the physics problems that deal with springs, I don't think anyone particularly likes them. But there you go. But you get the fact that there's a spring constant. So if you're just tugging on one rope, it has a spring constant EA over L. But if you're tugging on both the ropes, it would be like just having, let's say both these ropes were just kind of just one, but then the area is double. Area is twice that. So now what's your spring constant? Well, it's going to be E times 2 times the original area divided by the same length. So how does that relate to EA over L, which was our original spring constant? Well, it's just 2 times the spring constant. So when both these are acting, yeah, you just have a spring constant of 2K. So we're just going to say EA over L is K, so this is 2K. And then, but then what happens? Because after this first rope hits its max, it can't act as a spring no more. You know what I mean? It actually doesn't... It can hold, it's kind of fascinating. It can hold that max force, but when you put more force in it, this number doesn't go up. The whole idea of a spring is the second that you change its length, well, you increase the force, the tension. So you change the length again, increase the force. But we're saying once that's maxed out, we're still changing the length that this number didn't go up. So it's just back to that second cord being elastic. And it's just back to the spring constant of EA over L. Alright, so hell yeah. So we're going to take this to Excel, and I'm just going to show you how I graph it in Excel, because there is a little bit of a hiccup in Excel that maybe you can... but anyway, let's do it. Alright, so I got to edit my own videos, and we got to see what the problem was asking. It was saying, hey, we're going to put the force in the cable by adding weight, you know what I mean? So just going back to what the problem was saying is like, hey, we're going to put that 19,200 newtons of weight inside this bucket. Well, guess what? The slack is just caught. This other cable has force of 0, but this has 19,200. And then we actually skipped this 24,000 mark. That was just kind of a placeholder to figure out the problem with one cable. But then we go up to that 28,800 newtons. That's when this first cable shot. You know what I mean? It can't take any more force. It's changing. It's totally plastic now. It can hold that 24,000, but can't take anything more. But obviously at that point, the other cable has some tension in it too. And so, but this number is the weight we're putting in. When we put that much weight, a W, into the bucket, first cable gets fully stretched, can't take no more force, and the other one has that 4,800. Okay, and now let's say we load the bucket up to a max of 48,000 newtons. Well, now both cables are right at their limit. Sorry about that. And then I always like to go one step further, especially with these plastic problems. Let's load the bucket up with 60,000 newtons. Well, now what? Well, it can't take. This is the most it can take, and we're going to look over those charts in a second. And this thing is just going to stretch until it stretches and breaks. Now, I will add this. The change in length, we're talking a change in length of 125 millimeters for a 40-meter length. Well, elastic change in length, for even up to yield, is a very small quantity. It's like 0.2% for a lot of the, and if this is steel, and especially cables, we could easily stretch 5%, if not 20%, before these cables will break. Maybe even 30% before these cables will break. So, I mean, we're talking, you would have to take 120 and then times 10, so we would have like 1,000 millimeters. That's 1 meter just to get up to like 2%. And we're saying we could stretch this 20%. I mean, it's pretty wild. But let's say we just stretch it 5%. Well, definitely we could stretch this 2 meters. So just doing those mental math calculations in your head to be like, whoa, because like exactly, we're so wrapped up into this elastic. We're trying not to kill people. But yeah, those change in lengths are real small. But the cool thing is we use those small change in lengths for that force of the spring, K, change in length. We use that spring equation to find these forces, which is great. But then at the end of the day, just know that when things can move plastically, especially for these plastic problems, I mean, yeah, they can move hella. They can't take any more force, but they can definitely move way more than the change in length that gets them to that max. Okay, so now we're going to go over the charts and finish this video. Alright, hell yeah. So we graphed this in Excel. So we have our points. This is change in millimeters. So at 0, 0, there you go. At 100 millimeters of change, we go up to that 19,200. That's that. And then at 125, we were saying, well, if we just had one rope, we would just follow this line to about here, and then we would have like 24,000. That would be half of this max value. But because the other one kicks in, this line goes steeper. The slope of this line is that two times. The slope of this line is twice the slope of that line. So that's what we're going to see. But once that's maxed out, can't do no more. And then so just that other the other cable has a slope of EA over L. So in Excel, what I do is I want a trend line for each of these. So I just took those 2 points, and the only bummer is that I got to throw an extra, I got to duplicate the original. So, and we'll see that in a second. But then I have a trend line, so this is 192, and that's the slope of that line. And that's going to be EA over L. You know what I mean? So that's this 192 is the modulus of elasticity, which was 160 gigapascals. Area was 48 millimeters squared. You got to divide that by 10 to the 6 and divide it by the length of 40. Then you get that. But there you go. So this slope of this line is the spring constant. It's the EA divided by L term. But now we go to here and we see that the spring constant's double. 192 goes to 384, and then that final slope is over here. And then so what I did was we're just going to duplicate this final slope. But if I go into Excel, first, how do you do a trend line? Well, you right click on here and then format trend line. This comes up over here, and then you want to display the equation on the chart, and then it's linear. So there you go. So we have the equation on the chart. Now I want to show you just in Excel. If I just wanted to plot those 2 points, I don't know why it doesn't do this, but if I just go to the scatter chart, it just messes it all up. You know what I mean? You're just like, what up? And so let's get rid of that. And so I'm just going to insert a new cell, and I just copy this first value. And if I do that, then everything's just money. I can go to insert scatter chart, and I can just make a scatter plot of 2 points, and now it's perfect. And so we're going to also just right click, add trend line, and then over here, this is cool because you could do anything, polynomial, but linear, and we're going to display the equation on the chart. Hell yeah, because we just want the slope. But that's a cool way to do these material mechanics problems and then take them to Excel and then learn a little bit more. All right, so thanks for joining me, and guess what? That's a video.